Well, welcome to your Chapter 3, Transmission Basics and Networking Media. This evening or today we're going to be covering the basics of network media and the transmission basics. We'll be talking about full duplex, attenuation, latency, noise, different types of cabling, shielded twisted pair, unshielded twisted pair, fiber optics. Still need to cover a little bit about coax because it's still out there. You're still going to run into it. We're going to talk about advantages and disadvantages of these cables. May or may not talk about the serial cables because for the most part on our networks today we use them mainly for control purposes and not actually, I say control, I mean like programming devices and things of that nature. We don't typically use those today for networking anymore. And we're going to talk about the cabling in the workstation area, but most of that would then actually be covered in an actual cabling class, which you will get in your CNT 140 class. First thing I want to talk about is transmit. It's transmit, and you should also transmit and receive, because the whole point of it is we need to get our data from point A to point B. We transmit our data from point A to point B, whether we're doing it wirelessly, whether we are doing it over a copper medium, whether we're doing it over fiber optics. Okay, getting our data from point A to point B is simply known as transmit. Okay, the process of transmitting is called our transmission, and if we're going to transmit it, we also have to be able to receive it. Now, every networking device out there has to have a device called a transceiver on it, and it's really just a compound word, which means transceive or transmit and receive. So each one of our devices will have a transceiver, whether it be your network card or your switch or whatever. Okay. The characteristics of the data itself as it goes across the medium that we've chosen is going to be an analog or digital. Analog, if it was on a broadband transmission going across, say, your cable network to get to your house, it's going to be analog transmission. It's going to be analog transmission or a radio signal as it comes out of a wireless device. If it's going to be going across our copper, it's going to be a volt, okay, which is measured in electrical pressure, like your amperage. Either way, we're going to be sending a signal out on our networks, whether it's going to be pulses of light, a radio, or an electromagnetic wave, or an electrical pulse. Okay, these are called our signals. Now, if you have an oscilloscope, you'll be able to see an analog signal, and the analog signal is a sound wave. Now, the problem with sound waves is that they are easily distorted, but they have subtleties in them. Now, when we say that, it's kind of like how you're hearing my voice now. It's not like a speak and spell. It's not that drab digital robot voice like you hear in the movies. There are inflections in my voice. Where I emphasize different words. Those are things that are not digital. When we send those signals out over a digital wave, that is, those inflections, they are captured and then converted back into analog for audio purposes. The problem with that, as I mentioned earlier, is with the analog signal is that it is so susceptible to noise that the transmission itself can end up being flawed and misconstrued by the receiver, thus giving us bad data. Digital is, well, it's perfect. It's a 1 or it's a 0. It's on or it's off. It's true or it's false. It's math. It's right or it's wrong. And that's the beauty of a digital signal. Here's an example of a digital signal. As you can see here, it's a 1, okay, and here it's a 0, and it's a 1, and it's a 0. And what we do is we send a number of this in a given time. Okay, so X amount of data goes in a given time based on how many bits per second we're going to be sending. And when we get to that time period, we say, okay, stop. We take the information and we encode those into information. So if we have 8 bits, which equals 1 byte, that's how we break it down. We work in bits and bytes in our world. And the way it would work would be the first column here on the left, it has a value of 128. See, there's 8 of them. 1, 2, 3, 4, 5, 6, 7, and 8. Because we have to count our 0 as a placeholder. This column here has a value of 1. Okay? 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. And so on. So if we look at it that way, we have a place value. Each one of these is a placeholder, and it has a value. So for example, just looking up here, we have 1, 2, 3, 4, 5, 6, 7. So we have 7 values. This will be your 8th one right here, be a 0. So in that case here, this would be my farthest one to the left, my column right here. Okay, 8th column. It's got a bit position of 7. So 128 points. Then I have no points. And then I have 32 points. Then I have no points. Then I have 8 points. Okay, see how it goes across? And you would add all those up at the end. So if we did that, and we said, okay, let's just add something up here. And we said, okay, let's take 134. And this, I'm writing with my my mouse here, so it's not as easy. And we said, okay, 134. What would 134 look like if we were in binary? Well, you ask yourself some simple questions. Start from left to right. Say, okay, this column here. Does this column here fit into 134? And you'll say, oh, yes, it does. So, okay, 1. So we take that 128 and we subtract it from the 134. And we'll say that equals 6. Okay? Then we ask ourselves another question. Go to the next column. Does 64 go into 6? No, it does not go into 6. And does 32 go into 6? No, it does not go in there. And does 16 go into 6? No, it does not. Does 8 go into 6? No, it does not. Does 4 go into 6? Yes, 4 does go into 6. So we subtract the 4 from the 6, and now we have 2. Does the 2 go into 6? Yes, it does. Subtract the 2, or 2 go into the 4, sorry. Yes, it does. Subtract that out. We have 0. Does and that actually just finishes it up because the next column here is a 1, so we'll say no. So this right here, folks, this is the binary representation of 134. We make this so hard, but it's actually so stinking easy because it just has everything as a placeholder. And that's how we convert it by hand. You can convert it using a calculator. You open up Windows 10, okay, for those of you who have Windows 10, and you open up the calculator, and then over here, you can convert I think it's going to be our programming calculator here. Yep. So you have your decimal right here. And you say 134. And in binary, that's 1000110. Exactly what we came up with in the previous screen. We can do it by using a calculator. We can do it by hand. But I will tell you this, for those of you who are looking to take your Cisco exams or your Network Plus exams, you have to do this by hand. So we have worksheets online that are due for you that you guys have to do. There we go with chapter 3, and those are your binary to decimal worksheets. We will cover that again when we get to next time we see each other in class. Okay. So the benefits of doing analog or for digital over an analog signal are, one, it's just more reliable. See, over time that analog signal tends to fade. Think of it when somebody's further away from you and they're yelling. The further away they are, the less you can hear them. And that's what really happens when it comes to an analog signal. Okay, the signal weakens over time, and we can't hear it. But we can amplify. So you can put a repeater in between. But think of that repeater on an analog signal. It can end up being like whisper down the lane, where eventually at the end of the run, we don't really truly know what was said, because that message got passed along, and passed along, but did it get passed along correctly? And that's one of the disadvantages that we have with an analog signal. The disadvantage for a digital signal is that it takes more energy to send out our data. And as I mentioned last week when we were talking about the OSI reference model and how data got from point A to point B, and how the data was still pretty much the same darn size, but by the time we got to putting it on the wire, we had all that extra overhead and information that was in there. And that's one of the things that we have to look at when we're sending out our data and our information. Okay. Data itself has to be digital. Computers read, it's machine code. Computers only read zeros and ones. It's just the way it is. Okay. So we have to look at our data or a digital transmission as what the machine needs to be able to read. And a network connection can handle analog signals, but the machine itself has to be able to read digital. So then we're going to put one of these bad boys in there, okay? We're going to put a modem in there, because a modem, it does two things, okay? It takes that analog signal, and it'll convert it to a digital signal so the computer can read it. And the computer wants to talk, it'll take that digital signal, it'll convert it back into an analog signal. And that's called modulation demodulation. And that's really just a conversion of analog to digital. Think of what your cable modem does. You see that coax cable coming into your house is an analog signal. I know they told you it was a digital cable, but it's an analog signal coming in. And then it takes that signal, that cable modem does, and it converts it to a digital signal for a baseband transmission for your house to read. Does your cable box, your set-top box, does the same thing. It converts that signal, that digital signal, or analog signal, to a digital signal for your digital TV to read. That's why you have that nice high-definition TV. After that, we've got something called frequency modulation. You've been using frequency modulations for as long as you can remember. Ever since you were able to sit in your parents' car and tell them to change the station because you didn't like what's on the radio. Well, folks, look at it. FM, frequency modulation. It's a signal being put out there on the radio waves, okay? And it's just a licensed station which you're allowed to listen to. You can listen to amplitude modulation too. Amplitude modulation, the big thing about that is it's the amount of pressure, the amount of amplitude, the amount of amperage that we're going to put the signal out there with. If you've ever listened to an AM radio during a storm, and you're going by, say, a telephone pole or a lightning strike is nearby, and that sound comes blasting through the speakers, that's because you're on AM radio and sent out in a different signal. Okay? But we had the same things occur with our own data lines. And then for those of us who have DSL, I'm sorry for all of you, but like your CenturyLink, okay, there's a different kind of modulation that we use for our digital subscriber lines. Okay. What's important to remember is, like our fiber optic cables, they're simplex, which means the signal itself can only travel in one direction. There is no receiving on these. It's me talking to you, you not talking back to me, period, the end. And then there's half duplex communication, which means it's like a walkie-talkie, and it's like a CB radio. Only one of us can communicate at a time. If one of us puts the send and receive button, then we're going to cut the other guy off. And then there's like a phone call. Phone call is like full duplex. We can both be having a conversation at the exact same time. That is full duplex communication. And that's the big difference between all of them. Well, that's what I'm going to cover for this first part of our lesson. I'm going to do these little 15-minute intervals. I'm going to put them all out on YouTube for us, and you guys can pull them in when you need them. All right? We're going to be starting off next with multiplexing. So I'll see you guys in a couple minutes. Get up, stretch your legs, get a drink of water.